Hi everyone. I want to try in this video an online homework problem that uses the value of pKa. Thus far, I don't think I've discussed pKa, but you could probably deduce that pKa equals the negative log of Ka from your pH equation, right? The pH equals the negative log of the H plus concentration or the hydronium concentration. So first I want to make sure that we know pKa, understand it, and um, well, understand why we use it more often than Ka. Now, those are your two problems that deal with pKa, but let me describe pKa values and why they're useful. If you recall, let's take a look at pH. pH has a scale. The pH scale is typically 0 to 14. And what does it tell? It tells the acidity and basicity of a solution. It tells how acidic or basic a solution is. But where are these values coming from? Well, we know that pH equals negative log of Ka, and if we're going in the other direction, we know that 10, where am I going to put this? 10 to the negative pH equals Ka. My brain, not Ka, H3O plus. And then 10 to the negative pH equals the concentration. And we've done problems going back and forth between pH and the concentration of hydronium. Well, let's take the pH of 0. pH of 0 is, what is the concentration of H2O plus when the pH is 0? We take that to the 0. I'm hoping it's not an error. Oh, it's 1. So we could go from, if this is a pH scale, 0 to 14, we go from 1.0 molar, okay, very acidic, pH is 0, to negative 14. Am I doing this right? Yep. To 1 times 10 to the minus 14 molar. Effectively, what this does, it puts it on a log scale, the hydronium concentrations. So now this, from 0 to 14, we can consider that on the log scale. And it's just easier, right? It's just easier to report the acidity of a solution using numbers from 0 to 14 rather than having to deal with very, very tiny numbers like 1 times 10 to the minus 14. Or even with neutral pH, the hydronium concentration will be 1 times 10 to the minus 7. Okay, so we're going to do the same trick with Ka, and I'm going to give you a typical pKa scale. I shouldn't use the word typical because they vary depending on the source. Sometimes, let's say we go as low as, pKa's can be negative. So let's go to negative 3.0 to as high as, you'll see molecules, not in this semester, but maybe in organic chemistry, where we have pKa's up to 60. What does that mean, though, right? Let's do the math. Again, now we have pKa equals negative log of the acidity constant. Okay, let me actually put these in boxes. And this one, solve for the hydronium concentration. pKa. And then to solve for Ka, we have 10 to the negative pKa equals Ka. Okay, so now we have this pKa scale. What Kas do those represent? And then maybe we could also figure out a trend. The stronger the acid, the lower the pK, or the higher the pK. We'll figure that out together. But the trend, not the trend, but the Ka equals. Well, let's just plug it into here. So we have 10 to the negative of a negative 3. So 10 to the 3 is 1,000. Okay, so that's high, right? We are favoring the products by roughly 1,000. It's roughly because we don't know, depending on the chemical equation of the acid, we don't know if there's exponents, right, for those concentrations. But typically there isn't, right? We have HA plus water, which is a liquid, doesn't factor into the Ka, goes to H3O plus. So everything here is a 1-to-1 ratio. Anyway, what if it's 60, right? What is the Ka there? Well, just take that 10 to the minus 60, and it's 1, right? 1 times 10 to the minus 60. 1 times 10 to the minus 60. So that is not very acidic. Not acidic at all, actually, because the Ka is so low. All right, so think about your trends. Stronger acids, we know dissociate or ionize nearly 100%. So stronger acids have high Kas and low pKas, sometimes even negative pKas. Not so much in general chemistry, but in organic chemistry, you may not be asked to memorize the pKas of maybe between, I don't know, 8 to 12 acids, but it'll be super, super useful if you do memorize those pKas. And I'll leave it at that. Shall we just remind ourselves of this trend? Very strong acids have low pKas. Memorize those two equations, but it's, again, that P is like an operation. It's a negative log of whatever value you have. Okay, finally, let's try problem 1. Calculate the percent dissociation. Okay, they could have asked us also calculate the pH, but here they're not. And they gave us the initial concentration of trimethylacetoic acid, and they gave us the pKa. Right? They didn't give us the Ka, like we did when we were working with ice tables. Let me show you how I would summarize this problem, though. This is problem 1. Let me summarize it on this second sheet. We have a question mark, percent dissociation, and our givens are, we have C4H9, CO2H is the acid. It has a pKa equal to 5.03, and the initial concentration concentration in it, or initial, is 0.93 molar. We want percent dissociation. To get percent dissociation, we need how much of that acid broke up into its hydronium and anion. So understanding that this is your equation, C4H9CO2H plus H2O goes to H3O plus C4H9CO2 minus. Remember, net neutral reactants gives us net neutral products. The plus and minus cancel out. Percent dissociation is how much of this broke apart. Well, every one molecule of this that breaks apart gives you one molecule of that. So really we're solving for this concentration at equilibrium though, ICE. And why don't we just fill in this right away? 0.93 molar. All right, so when we want the percent dissociation, what do you really want? You want the part divided by the whole times 100%, and this part equals the concentration of H3O plus. Remember, for this ice table, we need Ka. We need Ka to get eventually this number right here. Okay, but we don't have Ka, we have pKa. We need Ka, we have pKa. You see the strategy? So the strategy is to figure out Ka and then do the ice table. What should we do first? Let's do the ice table first actually. We have 0, 0, minus x. Okay, some part of it dissociates. Plus x, x. We have x. Okay, that looks a little strange why I boxed that. We want the numerical value, right? And we have 0.93 minus x. Now, when you see a nice table like this, you could probably tell by now that you're headed towards the quadratic formula, but depending on this Ka, maybe we could use the x a small approximation. So why don't we take care of that now? We have, I'll just skip to the equation that I want to use. 10 to the minus pKa equals Ka. 10 to the minus 5.03 equals, oh, why don't I just do the calculation now? Minus 5.03 because it's the negative of the pKa. Let me get into scientific notation. It's small. 9.33 times 10 to the minus 6. So we are going to use the x a small approximation eventually. So we now have Ka equals H3O plus plus that anion C4H9CO2 minus over the equilibrium concentration of C4H9CO2H. But actually we don't need that. We don't need this numerical value. We need this one. But we're going to use this to make double check that x is small. So equals the calculated Ka that we just did, 9.33 times 10 to the minus 6 equals x squared over 0.93 minus x. This is familiar. You've done probably, between 5 to 10 of these already. X is small. Cross out that x. I'm not going to rewrite it. I'm just going to solve for x right away. Cross multiply. Oh, we got the number saved already. Times 0.93 square root of that answer. Okay, and it's tiny. 2.95 times 10 to the minus 3. So we got to make sure. Let's do the check now, actually. I'll do it here. The 5% rule. So 2.95 times 10 to the minus 3. And actually, if this is valid, we're actually not only checking for its validity, the x is small, but also we're doing this equation. Do you realize that? Because the part is this, and the whole is 0.93, the initial amount. And that's how we check. Because the x has to be 5% or less than the original amount. Or technically, the term that you eliminated, the minus x, has to be lower, 5% or lower than this 0.93. I only mention that because I know you've seen some problems where you minus 2x and you get rid of the 2x. So the 2x would be in the numerator. Anyway, oh, don't forget, times 100% equals times 100%, get out of scientific notation, 0.32%. So what we're actually done, because this tells me that it is valid, the x is small is valid, but also because that equation is literally this equation. We just solved for the dissociation. This is the dissociation. So this is the percent dissociation. Right, and that's what we wanted to solve for. What is the percent dissociation? Very tiny. But again, it's a weak acid. It's a weak acid because the Ka is very low, but also the pKa is positive. It's 5.03. So now we're getting a sense of, well, if an acid has a pKa of around 5, right, it has this much dissociation, less than a percent. Just for kicks, what is this pH actually? So we're going to take that x and take the negative log of it. So log of, where's x? Oh, it's this one. 2.95 times 10 to the negative 3. And then you multiply that by minus 1. 2, oh, that's a pH. 2.53. Pretty acidic. Pretty acidic for such a weak acid. Oh, you don't see that right here. Pretty acidic for such a weak acid, but again, remember, the pH is dependent not only on the acid strength, but the acid concentration. And this is almost 1 molar. 1 molar, right? I think we did that. See, 1 molar has a pH of 0. If that was a strong acid. Okay. Anyway, the answer is 0.32%. There's a second problem, and let me just put this as a record. Problem 2, you're going to do on your own. On your own. And actually, the answer is really tiny right there. Oh, good. Our problem 1, our answer was correct, 0.32%. Go ahead and do this problem 2. See if you do get 0.51%. Ah, Man, there's a typo here. So this is benzoic acid, and the pK of benzoic acid is 4.20.